Dr. Gold in the lab, Twitch stream glowing, formulas flashing, minds wide, knowledge flowing, equations on the board, numbers never sleep, teaching math and physics while them haters count sheep. Actual education, tune in and get schooled, flipping textbooks, breaking all the rules, from Newton to Einstein, concepts elevate. Keep the stream, it's the key to our fate. Dr. Gold dropping gems, knowledge raining down, actual education making scholars all around. Perpendicular minds, angles sharp as ice, maths and physics, yeah, the future's real nice. Got the Pythagorean triangles about to flex, quantum theories on deck, breaking all the specs, relativity theories, worlds getting small, grasp the universal laws, standing tall. From the atom to the cosmos, we rolling deep, grazing up the stars, no time to sleep. Black holes and supernovas, concepts we unfold, brain power heavy, yeah, that's Dr. Gold. Dr. Gold dropping gems, knowledge raining down, actual education making scholars all around. Perpendicular minds, angles sharp as ice, maths and physics, yeah, the future's real nice.
All right, what's up? What's up? Sorry, I was a couple minutes late today. Windows the Science
Hi.
update. Hey, Em, how's it going?
I'm good. How are you?
Good. Sorting out all the issues Kudu had with this exam. I'm so upset at it. So upset. Anyways,
Yeah.
no, I'm good. How are you doing?
I'm good. I had a question about the chapter 5 homework.
Okay, cool.
Can you explain number 12?
Sure, I sure can. Let's see, there we go. Okay, cool. There's that. Let me put this back here. Okay, and then... Alright, chapter 5. I need my chat to show here. Login. Come on. Chapter 5. Question 12. Oh, they want you to do a Taylor series expansion. Oh, wow. Okay, fine. I won't ever ask to do that on an exam. That's a lot. That's like an upper division, E&M question. But I'll show it to you. It's quite cool still. All right. It says a point charge Q is located at the center of a thin ring of radius R and uniformly distributed with charge. Okay. What is the electric field at a point lying on the axis of the ring at distance x from its center? Assume x is much greater than r. You can use Taylor series expansion with a small parameter r over x is much less than 1. Okay. So, they have this. And then there are two things that have charge. So you have a point charge here that's just Q, okay? This is positive Q. And then they say that this ring of charge has a total of minus Q on it. And then we're trying to figure out what the electric field is. Some distance x, which is right here. Okay, cool. All right. So there are two separate things providing electric field here. There's the ring of charge, and then there's also the point charge. So we're just going to add up what the electric field contributions would be for both things. So for a point charge, for this plus Q, what's the electric field that thing contributes?
KQ over X squared.
Good, perfect, yeah. So this is just KQ over X squared. And then we're going to assume everything is basically pointing in the X hat direction. Okay. Now for the ring of charge, I've done this derivation before. It's something you can kind of just look up, but what ends up happening is you have a bunch of electric field from each of these little pieces of charge along the ring, which we end up calling like DQ. And those contribute electric field that is symmetric in like the up-down direction. So any electric field component that points down, for instance, from the little bit of charge here, gets canceled out by the little bit of charge here that points electric field upwards. And there's an expression for this one. Let me just see. Electric field. It's like something to the 3/2. Electric field due to ring of charge. Yeah. I don't want the surface charge density. Where's just the regular one? Yeah, this is it. Okay, cool. Okay, so this is the derivation for how to solve for a ring of charge and the electric field at some point P. And so basically what you show is that, okay, for all of the electric field created from this, we're only going to have a component of the electric field that points in this direction. Because any electric field from, say, up top here, which has components that point like this and like this, the up-down component gets canceled out by any amount of charge here that's creating electric field that also has an up component to it. So how we figure out only what this component is we're going to say, okay, well, I want the electric field, but I want cosine of theta. Why are they saying sine theta? It's not sine of theta. It should be cosine theta. Maybe they're calling this the angle, though. One sec. Because then they're saying sine of theta is opposite. No, I don't want the y component. Where's cosine? Where's the cosine theta component? Ugh, maybe this one's wrong. People do the wrong thing sometimes. There we go. This is what I wanted. This is the correct solution. One sec, and then all this. And 2 pi r. Yeah, okay, here we go. This is it. Okay, right. This is, they do it in the z direction, but it's the same thing. So basically, you only care about the electric field that points up, and so that's going to be whatever the electric field is due to a little bit of charge here, times the cosine of this angle, theta. Because if this is electric field, cosine of theta picks out this amount, and cosine of theta ends up being the same thing as the
adjacent over the hypotenuse. So then, let's see. Yes, that's why this becomes z over z squared plus r prime squared to 3/2. Let me just rederive this. I don't like any of these derivations. Honestly, let me just do this. Let me do this my way. Sometimes I wanted to just take a shortcut and just get an answer, but all of them don't.
They don't do it the way I want to do it. All right. I'm going to do it this way. All right. I have some electric field, which I'm going to call dE. That is being contributed from a small amount of dQ here. Okay. And so that dE we know is equal to K dQ over R squared. Right, so this is the amount of electric field from a small amount of charge here to here. Does that make sense?
Yeah.
Okay, great. Okay. So, but this amount of dE, so that little infinitesimal amount of electric field, is pointing in two directions. It points in the up-down direction, but it also points in the x-hat direction. My argument is that when I look at every little bit of dQ here, that's going to have its own contribution, that it kind of forms like a TP, where any electric field that's pointing in this plane, like if it's pointing up or down or in and out of the page, it always has another bit on the other side of the circle, the other side of the ring, which is going to cancel itself out. So the only component that survives is the amount of electric field that points strictly to the right. Does that make sense?
Yeah.
Okay, so dEx is equal to K dQ over R squared, and then we're going to say times the cosine of theta. So remember, this whole vector here is dE. But if I want this component, and then let's say this is the angle theta, then the x component is this cosine theta. That's just how we break things down into components. All right, and then for theta, note that cosine of theta is equal to the adjacent over the hypotenuse, which for this triangle, the adjacent is x, and then the hypotenuse is whatever this distance is, which is, this is the r that actually we care about. That's the same thing here. This is also r. Okay, so, or let me use different colors, sorry. Let me use purple. Yeah, let's use purple. Okay, so from here to here, this is also called r. And because this angle right here, M, is the same as this angle right here, I can use this triangle to figure out what the cosine of theta is, even though it's really this triangle I care about for what the component of the electric field is along the adjacent side. So, cosine theta is adjacent over hypotenuse, so that's going to be equal to x over r. So now when I plug that in here, right, now I have, okay, so dEx is equal to K dQ, and then this is going to be all over r to the third. Okay?
Yeah.
All right. So now I can just integrate both sides. And because like this dQ doesn't depend on like this r is always the same everywhere, this integral actually comes out really nicely. If we really wanted to do it this is another way you could have done it. You could have said that, oh well, dq is the same thing as lambda ds, where this is linear charge density. So for instance, this is the amount of charge per unit length going all the way around the ring, and then this is kind of like the little arc length. But you end up getting the same thing, where you'd get, okay, well, Q is equal to lambda, and then the integral ds is just 2 pi r. And notice that, right, since linear charge density is equal to the amount of charge divided by the amount of length of charge there is, Q over 2 pi r, if you were to plug that in, you would still just get Q equals Q. Some other things they'll get complicated, and they'll say, oh, we have to integrate like across some angle phi to go all the way around. But you can just identify here that, oh, well, the little bit of dq, no matter where I am along the circle, that doesn't change any of the other variables. Like k doesn't change, it's a constant, and r is always just going to be what r is, because anytime I'm on the edge of the circle, I'm still located the same distance away from what this is. So that gets me that the electric field is equal to kq over r to the third, and then the key thing here is that r is equal to what is that going to be? Square root of x squared plus plus big R. Okay, so big R is the radius, is what they're saying. Okay. All right, this is big R. That's square root of x squared plus big R squared. So we should just get that electric field is equal to kq over x squared plus r squared all to the 3/2. I think that's the standard result for it.
Yeah, that's what I got too.
They said there's also a z component though. Where is that z coming from? One sec. Oh, wait. Oh, I forgot. When I put cosine of theta, right? It's x over r. Sorry, there's supposed to be an x here as well. Right? Cosine of theta is x over r.
Oh yeah.
Yeah, that's where I messed up. Okay, it's okay. Well, we just forgot it. Simple algebra mistakes. Okay, and I think that looks pretty similar to what we got. Yeah, because see, they have 2 pi r prime, 2 pi r prime times lambda. That's just q, and then you have qkz, and then they're using z instead of x. Okay. All right, so that's it. Yeah, so we did that correctly. Yes. Okay. Hopefully that derivation makes a little bit of sense, yeah?
Yeah.
Okay, so then E total is going to equal this one plus this one. So that's going to be kq over x squared. And then this is minus kqx over x squared plus big R squared to the 3/2. Okay, and now they want us to expand this for r over x is much less than 1. Okay. So I don't think we need to expand this. This is chill. This is the expansion they want us to do. They want us to do a Taylor expansion of this. Do you know what a Taylor expansion is? It's okay if you don't.
I learned about it, but I think I kind of forgot a lot of it.
It's okay. So how a Taylor expansion works is when you have a function that looks kind of weird, like it could be something like sine or cosine or e to the x, or in this case, if you have like, I don't know, like a plus x to like the 5/7 or something, like something going to like really weird powers, you can express this as a series of a bunch of really basic functions all added up all added up to each other. So, for instance, let's get a Taylor expansion for sine of x. Yeah, there we go. Or let me do Taylor Maclaurin series expansion common ones. There's some common ones you should know. There we go. That's all of them. Okay. So for instance, this function 1 over 1 minus x, you can also write as 1 plus x squared plus x to the third plus, well, this is wrong, plus x to the fourth plus x to the fifth. Do you see how these are much easier things to understand? You understand what, y equals 1 looks like, right? Just looks like this. Y equals x just looks like that. Y equals x squared looks like this. And so it so happens that if you were to add all these together and you just kept going up with the higher and higher powers, you eventually get a total function that looks exactly like 1 over 1 minus x.
Yeah.
Yeah. And you can do it for other things. So you can do it for cosine of x, looks something like this, e to the x, like this. And so calculating what these things are is figuring out what the Taylor series is for each one of them, which usually requires calculating like some derivatives and then plugging it into a formula. So this is the Taylor series expansion formula. Yep, there we go. So for a Taylor series, your function, and then they say this is like centered at A, is what they say. Centered at A, which just means like where in the function you're trying to approximate it, is equal to what the function is at A, and then you do the first derivative at A times x minus A, the second derivative at A over 2 factorial times x minus A squared, and then the third derivative over 3 factorial x minus A to the third, and so forth and so forth. And you just like keep adding these terms up and up and up.
Yeah,
So.
I think I kind of remember now.
Good, cool. All right, you're getting there. Awesome. Okay, so this I don't need to expand because this is very easy. Looks great. I feel like this one we want to expand out to x squared at some point, because then let's see. They want it. They want it all the way out to x to the fourth. Okay, we'll see. Okay, so let me think. And then they say, assume you can use the Taylor series expansion with a small parameter r over x is much less than 1. Okay. So they're saying that because where we're figuring out the electric field is much bigger than the radius of the ring, that x over r, r over x. So x is much bigger than r. So r over x should be basically very, very small. Let's see what I need to do to make this like look kind of nice. Okay, so I'm gonna say I just want to expand, I think, this part. So here we go. What is the expansion? Of x over x squared plus r squared to the 3/2 for r over x is much, much less than 1. I think I want to try to make, I want to try to see if I can get r over x to show up somewhere. So I think I'm going to like divide both sides by, I hate this, to the 3/2. Let me think. Okay. Yeah. Let me divide by x squared on both sides. So let me divide this by x squared. Let me divide this by x squared. And so effectively what I'm doing is I'm multiplying the whole thing by x squared. But then this is x squared to the 3/2. Do you remember what like x squared to the 3/2 is with math?
X cubed.
Good. Exactly, right, yeah. So this is going to end up coming out as x over x cubed. And then we're going to have 1 plus r squared over x squared to the 3/2. Okay? And so this
is going to end up being 1 over x squared. And this is 1 plus r squared over x squared to the 3/2. Okay?
Yeah.
Good so far? Alright, cool. Alright. I kind of see some cool things here,
I see like this is going to cancel with this. If I were to like, this almost looks like, what do they call it? Partial fractions, because I have 2 factors. I don't think I want to do that though. And r squared. Okay. I think I know what I want to do. Okay, 1 sec. I want Taylor expansion. And I think it's a binomial expansion. Alright, let's see. Yes. No, not that one. Where is it? Yeah, I think it's this. I think this is the expansion. I think I want to. I think this is also a binomial series. Let me think. Yeah, this is I think what I want. Okay. So, this is the Taylor expansion for 1 over 1 minus x to the a. Where in our case, a is going to be, or alpha is going to be equal to the 3/2. And our x is going to be minus r squared over x squared. Yeah. I think that's what's going to happen. So let's just look at what this part is. Or I want to say like basically just this. I don't think I care about this right now. Okay, so 1 over 1 plus r squared over x squared to the 3/2 is the same thing as 1 plus, and then we say alpha x, so that's going to be 3/2 x. And it's gonna be minus, because this is 1 minus x, and in our case, okay, I got you. Right, so this is gonna be 1 minus 3/2, and then this is gonna be r squared over x squared. Okay. And then I think the next one we just don't even care about, because it's going to be, if we say if r over x is much less than 1, then this squared is even more less than 1. Or like this to the 4th is like even more less than 1. Let's see. Okay. This would be 3/2 plus 1 over 2 factorial. And then again, this would also be a minus. And then this would be... no, this would be a plus, because x squared And then this would be r to the fourth over x to the fourth. Okay, cool. And that's all the terms. That's for this. So this whole thing is now equal to 1 over x squared. And then we would say 1 minus 3/2 r squared over x squared. And then plus, I'm going to say that this thing is basically 0, I think is what I want to say. I'll say this is basically 0. Do you understand why I'm going to say this one is 0? It's okay if you don't. I can explain it. I think it's because if r over x is much less than 1, then r squared over x squared is even more less than 1. And then r squared over x to the fourth is even more less than 1. So we just say it's basically equal to 0. This is... I know this is kind of annoying in physics. We say, like, to what point do we start calling things 0? And I think in this type of question, because it's multiple choice, and you see how everything's like x to the fourth or like x to the fifth, I think we have to say to ourselves, oh, if this is x to the fourth and then this is x squared is still left here, we're not going to have anything on with x to the sixth. So, okay, so that was that. And then this still came from here. So you have KQX. Or actually, let's pull the KQ. Let's pull the KQ. Let's pull the KQ out of both of these. Okay, so I'm gonna have KQ, and then from here, I have 1 over x squared minus 1 over x squared times 1 minus, and then this is plus. Okay. Okay, I think I see the right answer we're gonna get. So then this will cancel with this one. And then this is going to make two positive things. So I end up getting 3/2 KQ r squared over x to the fourth. Which was that answer choice C? Yeah, 3KQ r squared over x to the fourth. Okay, it is answer choice C. Okay, there it is, Emily.
Yeah, that makes sense.
Does it or does it not? Because I understand it's a lot. It's a huge pain of a problem. You can ask me what parts don't make sense, and I'm happy to go into it more.
I guess, like, would there ever be a point where, like, x is large enough that the r squared over x squared term also goes away, and then it just becomes like 0?
Yep. So yeah, no, and that's totally valid, M, right? So if I'm far enough away that this plus Q and this minus Q look like they're basically on top of each other, then yes, the electric field is basically 0, right? But do you see how that's a trivial answer, right? Or it's kind of it's like a non-answer, right? None of the answer choices here said that the electric field could be 0. So I think that's how you know that you have to keep at least this term. Yeah, you can't knock them both out, because you are correct. If you were far enough away, those two charges look like they just annihilate each other.
Yeah. Because initially when I was solving it, like, I got 0, so I was just like confused. Yeah.
Yeah, no, it's okay. It's this is like kind of one of the annoying things about physics sometimes, is they kind of hand wave to say, oh well, up to this point it's good enough. Up to this point it's good enough. Technically we could have also included this one, right? The issue with that is that on the answer choices, I don't have anything going up to x to the sixth. So I know that that's where they probably stopped.
Yeah.
Yeah.
Okay, that makes sense.
That makes sense? Yeah, you're not crazy. It's just, it's an annoying thing about physics questions sometimes. Trying to like guess like where they want you to stop.
Yeah, well, that makes sense though.
Okay, cool. And I appreciated going through this again, because I had to like remind myself how I do this.
All right, well, thank you.
You're very welcome, Emily. If you have any other questions, feel free. Otherwise, you can bounce. It's all good.
Okay, all right, bye.
Bye. Oh man, what a heater of a question there. I'm glad I got that one though. Mostly without any help. Sorry, what does it say? Sorry, what's up, Monkey Man? Sorry, I couldn't really respond much to chat. I was helping out a student there. Looks like Jeff and Monkey Man are talking about machine learning and stuff. That's cool. Val upset. Oh no, the Rainbow Gang got to him. Wait, Zation, are you talking about soccer? Poor England did lose today. Although, I guess they played kind of poorly in the second half. They did this thing they did to Mexico where they're up 1 point and then they just hold it. Like, their defense, they just stop attacking. And then they just try to make their defense, like, win. Unfortunately, defenses eventually run out. And I think that's what happened when Argentina scored two points within like 5 minutes of each other. You were happy with today's result? Ireland, yeah. Oh, man. But yes. All right. Which part of Ireland is Boston in again? All right. Let's see. What's on the queue, which I haven't looked at since probably. Sorry, what was it? I had to fly out Thursday. Yeah, I think. Did we have office hours on Thursday? I don't think we did actually. Yeah, I think I had a flight on Thursday. Or no, I had a flight on Friday. We did have office hours. Did we? One second, I gotta go check. Keep myself like sane here. Yes, we did have office hours on Thursday. Okay. But then Friday I flew out, right? I was gone Friday, Saturday, Sunday. I was gone Monday, I was gone Tuesday. Today's my first day, like, kind of back. Starting to feel a bit more normal. What is today, Wednesday? Okay, cool. Getting there. Anyways. Oh. Let's see what's in the queue from 8,620 minutes ago. This was Zach's question. I think we did this one. Zach was asking about Gauss's law. Yeah, mark that one as done. Jeff hates applied statistics.
My name is Jeff.
And you barely understand this math thing.
Brother,
You understand this math thing more than you think you do, dude. Don't worry. Oh, wait, it marked... Wait, it marked... I marked yours wrong. Sorry, one sec. Oh, we did that one, though. Or did we? Did we do this one? I also hate stats. No, stats is great. Sorry, let me open up the Discord if you guys want to come in. Sorry. It's been an hour, right? It's basically been an hour. There we go. Boom, boom, boom. We actually finally got the heat wave today. And by heat wave, I say it's in the 80s, which is still too hot for Los Angeles. What's the weather? Yeah, 70. It's we. I love how they call this a heat advisory for us. Heat advisory. Oh, temperature's up to 104. Yeah, not by me though. Maybe if I was in downtown LA. Yeah, there we go. 86. Yeah, this is getting warmer. Trying to think, where would it be the absolute hottest in SoCal? I want to say like Northridge. There we go, 99. Yeah, Northridge, Los Angeles. Yeah, this is where it gets hot. Well, Death Valley is definitely the hottest, but I'm thinking in southern. Death Valley is not in Southern California, is it? It's kind of like in the desert. But yeah, so the funny thing about like dude, Northridge is not that much further from me, honestly. Here, Northridge. Stop. So yeah, for instance, I live like right over here. Northridge is over here. This is 104 and this is 80. So, I mean, if I wanted to drive to Northridge right now from my house, well, it's only 20 miles away. It's an hour because of traffic.
You done messed up, Aaron!
But it's crazy. It's a 20 degrees. It's crazy. 80 degrees is winter weather, yeah. Yeah. Santa Monica's probably 75, even nicer, yeah. Have you been to the Bay Area? San Jose is like 20. Yeah, you're right, actually. And that's actually where I was, Jeff, for
My name is Jeff.
for Monday and Tuesday. I had a like a last minute work conference thing in San Jose. And it was hot compared to I'd been in like San Francisco earlier. It was actually quite nice. What's up, Meezan?
That's dope.
Meezan, how your call jobs going, dude? I appreciate the server boost, by the way. We now have pretty usernames because of Meezan. Love that. Okay, but let me see. This was a question. I'll spend a couple minutes on this one. I'll try to do this one. Let R be differentiable function such that f prime of x plus f of x is equal to the integral from 0 to 2 of f of t dt. If f of 0 is equal to e to the minus 2, then 2f of 0 minus f of 2 is equal to what? You solved this one, Fembox? Is it tough? Is it scary? I don't know. F of 0 minus f of 2. And f of 0 is equal to e to the minus 2. It's really just a second order differential equation. If you, I would see that. I don't like the integral here, right? How do I get rid of integrals? I take derivatives. But wait, if I do d dx of this is a constant, no? I'm gonna assume that f prime it means d dx, okay. Because this is a definite integral. Yeah, they went great. Ended up going to SLO. Nice, dude. SLO's a great school. Beautiful place.
Who's getting baby voice on here, dude? I thought I had limits on baby voice. Yes, I will hydrate. Nice, Cal Poly SLO. Yeah, C-Slub. Or no, sorry, that's Cal State Long Beach is what I'm thinking about. SLO is up in San Luis Obispo. I've been there before. It's on the way to Paso Robles. Beautiful campus. You're right there on the beach. And I think they have a really good engineering program, actually, from what I remember hearing.
They also are one of the few universities, I think, to offer a degree in wine tasting. Because there's so much wine. There's so much wine up there. But yeah, I feel like this one isn't that bad, right? I feel like if we do ddx of this side and ddx of this side, this is a constant. This just goes to 0. So you get f double prime of x plus f prime of x is equal to 0, right? Okay, that's super cool. So what do you say? So let f equal e to the ax, right? So f prime is equal to a e to the ax. F double prime is equal to a squared e to the ax. So then you get a squared e to the ax plus a e to the ax is equal to 0. This cancels. Great aerospace. You liked it better than UCSD? Great.
Oh, yeah.
You don't think the derivative helps very much? Why not, dude? Bro, don't I get this? Like, a squared plus a is equal to 0. So a times a plus 1 is equal to 0. So either a equals 0 or negative 1. So, I don't know. I feel like f of x is equal to c1 plus c2 e to the minus x, no? Yeah, I would have thought UCSD would be closer to industry and stuff. But yeah, if you went and you visited and you liked Polyslow better, then yeah, great. Cork. It's always Cork. Okay. And f of 0 is equal to e to the minus 2. So what does that tell me? That tells me that C1 plus C2 is equal to e to the minus 2. Okay, so then 2f0 minus f of 2 okay. So f of 0 is equal to c1 plus c2, right? And then minus f of 2, so minus c1 plus c2 e to the minus 2. Oh, it's not very nice, is it, right? Well, 2c1 minus c1, that's just c1. And then this is plus 2c2 minus c2 e to the minus 2. Man. But I don't know what C2 is. Fuck. Nice. Yeah, slow's better for the... He's more quiet. Yes. And a lot of good opportunities. Excellent. Yeah. That's why I say it's very important to go actually visit the college and like get an idea for the atmosphere. For instance, when I was going to grad school, I could have gone to UCLA or I could have gone to Madison. And University of Wisconsin-Madison definitely has the quote-unquote better like plasma physics program. They have way more machines. It's across like 3 different departments. But I, don't really want to live in Wisconsin. So that's why I figured, well, I'm going to have a lot more fun and not hate myself if I live in a place with sun and great weather. And so that's why I chose Los Angeles. So yeah, if you're not a city person, the marginal benefit of, quote-unquote more industrial opportunities at UCSD will not outweigh your own mental health and performance in an environment that you actually enjoy, which I think, yes, slow is beautiful, dude. It's almost like too beautiful for me. Like I don't think I'd get any work done. I would just sit on the lawns and just enjoy the beauty all day. I don't think the derivative was the right move. Yeah, I don't think it was either.
Oh no.
Yeah, it didn't really work out for us here, did it? Because I need more boundary conditions, I think is what I need, right? Like I have f of 0, but I need like another f of something. That equation still needs to be solved by a reduction of order. What does that mean, reduction of order, Breasticles? I've been living in a box for 3 years. Yes, you have.
You done messed up, Aaron!
I remember you talking about your previous college experiences. Yes, enjoy, dude. You're gonna have so much fun with the green. It's so nice out there, dude. It's beautiful. Learn to surf, dude. There's great surf up there too. What's up, Breasticles? What are you talking about? Reduction of order?
I was gonna type, but I was just so tight. Reduction of order when you see something like f prime plus f double prime of x is when you would say like let it equal g or g of x equal f prime, and then you solve it, and then you plug back in, and then solve it again. But technically, the integral on the right is just a constant.
Correct.
And our original differential equation is a first order linear differential equation. So we can just solve it as a first order linear differential equation for whatever that constant is, and then just solve for the constant and then plug back in.
Okay. So this was my f of x. You're saying that I can just plug this back in to the integral?
I wouldn't use that f of x. You don't need to.
We don't like this f of x? What's wrong with it?
Nah, not particularly.
Why? What's wrong with it, dude? It's not cool?
Because you could. I would just, that, well, the integral on the right is a constant.
I know that. You're correct. So when I took the derivative with respect to x, that's why I went to 0.
Yeah, but you don't need to take the derivative. Just call that a constant. Just
call
it C or
I
A,
see.
I see.
Okay. All right. He's saying do this. Say f prime of x plus f of x. I'm super close, Gold. Thank you, Femvox. You're saying this is equal to C. Uh-huh. Okay, because yes, it is a constant.
And that's just a first order linear differential equation. We know how to solve that.
Do we? Do I?
Yeah. It's just the integrating factors.
Yes, yeah, that's what I was going to say. It's integrating factors, isn't it? Oh, man. That's the e to the integral of... Fuck me, dude. What is it?
They usually call it p of x. It's whatever function of x is outside of the
zeroth derivative?
Yeah, that's the word for it.
Yeah. Well, that's 1, right? Yeah, I think it's like p of x dx is what it is. But that's just e to the 1. No? It becomes e to the x. Yes. Thank you, Mizan. Yeah. Sorry, integral p of x dx is integral of 1 dx. Yes, that's equal to e to the x. Okay, so now I multiply everything by e to the x, right? So I get f prime of x, e to the x, plus e to the x, f of x is equal to c e to the x. And then I recognize that this is a product rule. So this is d dx of e to the x f of x is equal to c e to the x. Then I integrate. And so I get e to the x f of x is equal to the integral of c e to the x, which is just e to the x. So f of x is just equal to c? Right? Am I crazy? F of x equal to c. So then c is equal to... Let me think. Shouldn't it have an x on it? It's just a constant, dude. What the hell? E squared? Where are you getting e squared from? Because f of 0... Oh, yeah. F of 0 is equal to... No. Well, f of 0 is e to the minus 2. So I think c is equal to e to the minus 2.
Oh, I think I see kind of what happened.
Where's the error? What did I do wrong?
I would move the f of x over to the right, or yeah, I'd move the f of x over to the right side and do it by separable as a separable differential equation. Because now that I think we don't know what f of x is directly, so we technically don't know what p of x is.
Oh,
But it is separable. If you were to move the right hand side over.
you want me to move this over here, or are you saying
Yeah.
down here?
Yeah.
Okay, so we're not gonna.
up top.
So we're not gonna do integrating factors.
Yeah, I would do separable.
You done messed up, Aaron!
Can't do integrating factors anymore.
And then since we know that there's a general and a particular solution, we can start by just doing the homogeneous.
Okay. So I'm gonna say df dx is equal to c minus f of x. How am I gonna separate this though?
Do it C0 in this case. We want to start by just doing the homogeneous solution.
Okay.
Because there's a homogeneous solution and then a particular solution. And the particular solution will just become a constant for linear ones. And then so it'll be
Okay,
just
so
be,
f prime of x plus f of x is equal to 0. So cool. So df dx is equal to negative f of x. Okay. And then I'm confused.
once you move it over, you can say f prime of x over f of x. Equal to negative one.
Okay. My bad. Can we just show that f of x is equal to e, then minus 2 just works? Maybe. Let's see. Okay. Move it over. So f prime of x over f of x is equal to negative 1, right? Is that what we're saying? Okay.
And then we just integrate.
And then we just integrate.
Yeah.
Oh, okay. Is this this is ln of f, right? Okay. Fine. Okay. Yes. Okay. So this is ln of f of x is equal to negative x. So then f of x is equal to e to the negative x?
Yep.
Okay. Cool.
Oh, and then plus c.
Plus c, technically. Oh, well, times c, I guess, right?
You want to do plus c. Oh.
No, it's times c, right?
Yeah, it's times c. It's plus c on the ln. I was thinking the ln.
Yeah, there you go. Femvox says, boy, I wish you had plugged your f of x back in. Which f of x, Femvox? Are you talking about this one? Because, look, it is kind of the same fucking one, dude. It's the same one. It's alright. Can't you use the annihilator method? Dude, what's the annihilator method? Sounds like someone just like bashes the integral into submission. Okay.
Throw it in MATLAB.
So that's the homogeneous solution. How do I solve for the non-homogeneous again? Do I just plug in what f
In
of
this
x
case,
is?
it's just a constant. It's just another constant.
It's just another
so-
constant, right? Yeah.
Yeah, it's just another.
Because if I were to plug this back in, then I end up getting negative c e to the minus x plus c e to the minus x is equal to c. Well, this is just 0, dude. Okay. All right.
Well, yeah, that's because it's the homogeneous solution.
Right. Okay.
First
So just
order
plus C.
linear ODEs with the constant is just another constant.
Cowsheik Techno says the integrating factors way was good. Was it, man, though? I feel like it wasn't valid. Maybe not. Okay.
I'm sure
Okay.
there's probably a way, but like if f of x was 2x, then our p of x changes. Is the problem.
So here's my question. We're still back to where we started, which is I have this, and I only have f of 0 is equal to e to the minus 2. So that just tells me that c1 plus c2 is e to the minus 2. But I need to figure out what 2f of 0 is minus f of 2. How do I get f of 2? Unless... maybe I'm supposed to do something with this? You have to plug it back in to get more info, Fembox says. Okay. Okay, so let's do that. Let's do integral from 0 to 2. And then, okay, so this is now c1 plus c2 e to the minus x. Or e to the minus t, technically. dt. For the right-hand side. And so the integral of that, this is just going to be c1t from 0 to 2. And then this is going to be minus c2 e to the minus t from 0 to 2. I think so. Okay, cool. So then that tells me 2c1 minus 0c1. And then this is going to be minus c2 e to the minus 2 plus c2. Because then e to the minus 0 is just 1. Okay, so that's the right-hand side. And all of that is equal to f prime of x plus f of x. Okay, so maybe this tells me something. Well, f of x was equal to this. And f prime of x is just the derivative of that. So that's just going to be negative c2 e to the minus x. What does that tell me, though, ladies and gentlemen? What does it tell me? Because this cancels. Okay, so then I get 0 is equal to c1 minus c2 e to the minus 2 plus c2. Oh. Isn't that what this was? Isn't that literally what I was looking for? I feel like it is what I was looking for. Right? F of 0 was just e to the minus 2, which was just equal to c1 plus c2. And then f of 2 was c1 plus c2 e to the minus 2. This is what we were solving for. We're looking for this eventually. So then 2c1 minus c1 is a single c1. 2c2 is there. And then I get minus 2. Oh, this should be a minus 2. So this is what I wanted. What I figured out from plugging into the integral here is that c1 is equal to, not minus 2, minus 1 was right there. Oh, yeah, you're right. You're right. You're right, Fembox, sorry. Yeah, this is just a minus 1. Sorry, I don't know why I saw another 2 on there. Okay. But then when I plugged everything back in, I got c1 is equal to 2c1. Move that over, I get a single c1. And then I had minus c2 e to the minus 2 plus c2. This is all equal to 0. So this and like part of that and then that is all equal to 0. So I just need to figure out c2 then, maybe? I don't know, man. Okay. That's true. And then c1 plus c2 is equal to e to the minus 2. Yeah, so my answer is just c2, right? Right, because c1 plus c2 is e to the minus 2. Oh, man. Oh, wait. 0 is equal to e to the minus 2 minus c2 e to the minus 2. So c2 equals 1. Bingo. Okay. And then from this... e to the 2 minus 1. Okay, cool. So then, okay, now we can plug things into here. Great. Okay, so then C1, so we get e to the minus 2 minus 1 plus 2 minus e to the minus 2. Cancel, cancel. Minus 2 plus 1. Minus 2 plus 2. Minus 1 plus 2. Final answer is equal to 1. Nice. There we go.
Well done! Well done!
Wow. Cool. Answer was 1. What a crazy question there, Kaushik Techno. I did like how we did a couple different integration methods. We did integrating factors. Yeah, very cool question. We did. Oh, we just take the derivative, and then we're like, oh, let's actually like solve it. Then we did separable differential equations. We all kind of kept getting the same thing. I think the key way to fix this was figuring out, oh, let me like plug back in for the right hand side, and then I'll get another equation that relates C1 and C2, and then I can solve for C1 and C2. Cool. Yeah, very interesting. Okay.
I asked ChatGPT. I see what we did wrong for the integrating factor. It actually would have worked.
What did we do wrong?
We should have integrated from 0 to x rather than integrating and doing an indefinite integral. We should have done 0 to x, and that would have given us that e to the x times f of x minus f naught is equal to c times e to the x minus 1.
You mean when we were doing this integral right here? We should have done 0 to x? Why? Just curious. Is there a reason?
Let me ask chat. I don't know.
Yeah, chat. Why do we want to do that?
It works. I imagine it has to do with the boundary conditions, but I don't have an answer that I'm confident enough in without asking.
Okay, you want to do yours, Rascals, from a while back? This, like, horrendous integral?
Oh, yeah, I stole that from Winklebot.
Winklebot? What's Winklebot, dude?
And Zach server. He's a guy in Zach server. He was working on that one.
Okay.
I was like, this is a fun one.
Negative x to the e to the 2 plus x to the e to the minus 2 over... Oh, this is like an infinite series on the bottom, no?
Mm-hmm. Yeah, it is. It says we do it indefinite just from the boundary conditions. Because we already know the boundary conditions, we can just do 0 to x. It's more convenient.
Okay. Femvox says, I looked at this one for a while and I got nowhere.
This one's peak. It's not as bad as it seems.
Okay. My gut instinct is to try to represent this as a series, I guess.
Yeah.
This looks like
definitely the first thing you want to do.
Yeah, this part right here looks like sum from n equals 0 to infinity of 1 minus x to the n all over n. I feel like it does. Yeah.
Mhm.
Okay. You want to say it's because it's Mr. Breasticles, you think we're going to need hyperbolics?
No, not actually on this one. But it is another one of my favorite tricks. Favorite tricks
Okay.
of all time.
I want to say it's the Feynman trick. That's your favorite
Well,
trick,
see,
no?
It is my favorite trick.
Okay.
We'll get
So,
there,
okay, we'll get there. So I have 0 to 1, negative x to the e squared plus x to the e to the minus 2. And then we're going to say all over this series. Cowcheek's like, observe that the denominator is ln of 1 minus 1 over x. Okay. Does this look like a nice little series? Is it? Maclaurin series we were talking about,
I
right?
think it's supposed to be 1 minus 1 plus x, actually. But yes, it is. It does look a lot.
Looks kind of like this one, right? Funny, we were just going over Taylor series with one of my students. Okay, so yes. 1 minus smells loggy. Yes. This looks like x is equal to 1 minus n. I don't know about the flippy floppy though. How are we gonna get the flippy floppy to go away? Oh, I guess if it's negative. Yes. Okay, okay. The way, notice how this series doesn't flip-flop. Or wait, does it? No, it doesn't, right? Minus, plus, plus. I assume the next one's plus as well, right?
Yeah, it should all be plus.
Okay. So I need this thing to go away. And I think, yeah, so if we do ln of 1 minus x. It's actually here. Let me call it u. I think is what I want to do. So that this is now x is equal to negative 1 minus u for this thing. Then we have the sum from n equals 0 to infinity. It's going to be negative 1 to the n plus 1. And now x is going to be negative 1 minus u. But then this is all to the n. So this is the same thing as negative 1. One second, let me move this over. So this is the same thing as n equals 0 to infinity. Negative 1 to the n plus 1. Negative 1 to the n. 1 minus u to the n all over n. And then this will cancel out. Ooh, wait. There's a negative sign on it, though. Because that's going to be a negative 1 to the n, negative 1 to the n. Cool, that cancels. But then I have negative 1 to the 1. Okay. So, in fact, I think this is negative ln of 1 minus x.
Mhm.
Okay, cool.
Which is just negative ln of x.
Oh, okay, yeah, sorry. So, negative ln of 1 minus 1 plus x, right? This cancels. And so we just get negative ln of x. Oh, that's very cool. Okay. Is that what I'm supposed to do?
Yeah, that's where it presses.
Oh, baller, dude. Okay, cool. So we get negative x to the e squared plus x to the e to the minus 2. And then this is all over negative ln of x. And then this is still dx, I guess. Oh boy. Oh boy. Okay. Oh, I don't like integrating ln of x, honestly. I really don't.
Yeah, that's the fun part. You don't have to.
You don't have to.
Well,
Okay.
You're not gonna have to. No.
We're not gonna have
This
to.
is where the magic comes in. So
Should I
break the
Split
integral.
it into two,
into
right? Let's split it
separate
into two.
integrals. Yep.
I agree with that. Let's do that. X to the e squared over ln of x. And then we're going to say minus x to the e to the negative 2. Now use Feynman. You spelled Feynman wrong, Kaushik. F-E-Y. F-E-Y-N. Okay. Cool.
There should be a negative on the second one. It should be a minus.
Yes. Sorry, this should have been minus. Right, from this and this.
Okay, now we just want to look at one integral, and we want to say, right, if x were a parameter alpha, we could figure out this integral. So we'll call it the integral from 0 to 1 of x to the alpha over ln of x.
Oh, okay. I see. Okay. Let this be a parameter. Okay. Okay, so I'm gonna say f of alpha is equal to 0 to 1 x. Oh, I see, because then this is also to the alpha. Okay.
Mm-hmm. And we
Nice.
can just
Okay.
plug in our alpha values.
ln of x dx. And then I think I'm going to do dd alpha, right? Is that the trick?
Mm-hmm.
Okay.
And this is like the most famous like elementary example of Feynman's trick. You
So,
see like everywhere.
We're gonna move that inside the integral. And then I'm going to do this. So derivative of x, so oh man. Oh, this is an ln
remember,
thing.
It's a partial derivative.
Yeah.
Sure.
Yeah, this is cool because sorry. d dx of a to the x is equal to a to the x ln of a, right?
Mm-hmm.
So this is going to become, so first of all, this is going to just become, I don't know, f
Just
prime,
F
of,
prime
alpha.
of alpha.
Cool. This is going to still be 0 to 1. But now this is going to be x to the alpha ln of x to the alpha.
Just x.
Yes. ln of x. You're right, actually. Right. It's because it's ln of a, but a in this case is x.
Mm-hmm.
Oh, beautiful. Goes away. Okay, so then I get f prime of x. Oh, this is very cool. So 0 to 1, x to the alpha, dx. So that's going to be x to the alpha plus 1 over alpha plus 1.
Yeah, that sounds correct.
Right? Raise the power, divide by the new one. Evaluated from 0 to 1. In terms of x. Okay.
Yeah, or x, y.
So that's going to be 1 to the alpha plus 1. Oh, the other one's just 0 then. I don't really care about it. Okay.
Yeah.
Over alpha plus 1. Okay.
And then now this is really easy to integrate.
Oh, sorry. This is f prime of alpha, not f prime of x. Sorry. Thank you, Kaushik. My alphas start learning like CXs. Okay, there we go. Okay. So, So then, df is equal to 1 to the alpha plus 1 over
Which is just
alpha.
1.
Which is just 1. You're right. Yeah, this is always just 1. Cool. Awesome. Oh, this is very, very cool.
That's dope.
Because it's alpha plus 1 d alpha. And so this is just ln of alpha plus 1.
Mm-hmm.
Technically plus c though, right? Is there a constant in there?
I don't think we need to worry about the constant.
I don't think we're gonna worry about it.
I don't think there is.
Okay. So f of alpha is equal to ln of alpha plus 1. Okay, cool. All right. So let's bring this back. Kaushik's telling me he's like, there's a plus C, dog.
I mean, there is, but if I remember correctly, it disappears when we evaluate our boundary conditions.
Yeah, because I think they subtract each other. Right, because we said f of alpha of f. Blah, blah, blah. Okay. Okay, we said f of alpha was equal to all this. I don't know why this got like really mangled, dude. What the hell? Oh, I can't even draw integrals today. Okay. 0 to 1. Okay, so then this right here, that's f of e squared, right?
Mm-hmm.
And then this is f of e to the minus 2.
Mm-hmm.
But f of alpha is equal to this. So we get ln of e squared plus 1 minus ln of e squared e to the minus 2 plus 1, which I can combine as a single log. So ln of e squared plus 1 over 1 over e squared plus 1. I don't know, multiply top and bottom by e squared. So you get ln of e to the 4th plus e squared over 1 plus e squared, I guess, maybe. Looks kind of nicer. Yeah?
Yeah, let me check. You should get 2. I mean, you got the right part there. There's just... I don't remember what the simplification was. It should be 2, but there's...
The answer's 2?
You got the correct... Yeah, you got the correct, like, ln there, the e squared plus 1 over e to the negative 2 plus 1. I just forget exactly how it simplifies.
Ah. Kaushik says this turns out to be 2. Yeah, how does this turn out to be 2, dog? Tell me. Factor out an e squared. Okay. Sure. Ln of e squared. That's e squared plus 1. Oh, duh.
Oh,
Yeah.
yeah.
Oh, yeah. Okay, I see it now. Okay, this cancels. That's just 1. And then we have ln of e squared. Pull the 2 out. 2 ln of e, which is equal to 2. We did it. Great job, everybody. I feel really good about that one.
What's up, Mitch?
Wow, very cool question. I like that one. Had a lot of interesting parts to it. Feynman's technique. That took us 14 minutes. Estimated time of completion was 20. Wow, we beat the estimation for once. Isn't that crazy? I think it's because I did have some significant help though.
Yeah, I mean, though once you realize that it's negative ln of x, it gets pretty easy.
Yeah, this is a really cool trick. They kind of hid this, right? They made this look like really, really weird, and then only when I did this could I figure out, oh, it's literally negative ln of x.
Yeah, and those x to the n over ln of x integrals are really common.
Are you saying these?
Yeah, anything that looks like that, where it's like a x to the something over a ln of something, is like pretty famously known for Feynman's trick.
I guess because of this. Because derivative of a to the x is just a to the x ln of a.
Yeah, exactly. And I think I want to say it's the only way to solve that integral. I don't know if there's another way, but it's the only way I know
That was cool.
to solve an integral of that form.
Yeah, that's cool. Very cool. Look at all that. Pretty colors. Nice. Okay, cool. All right, let's see. I already did Zach's. See, what do you got me for free, Fenvox? Let's do one of yours. Find the shaded area. What's the Trappist 1 system, dude? What's the Trappist 1 system? A planetary system located roughly 40 light years away, sorry. In the Aquarius constellation, it consists of 7 rocky Earth-sized exoplanets orbiting a single ultra-cool dwarf star. 3 of these planets orbit within the star's habitable zone, making it a prime target for extraterrestrial life. Yeah, the only problem is that, like, even if something was going at the speed of light, it would take us 40 years to get there. That's why we need, like, warp drives. Right, things are too hot in the red zone, right? They're too cool in the blue zone. Peter Dinklage? What does Peter Dinklage have to do with it? Oh, dwarf. Oh. I've been on quite a Game of Thrones kick lately with all this House of the Dragon stuff. Oh, they may have been PC. I don't care. Whatever. Stop. I think it's literally the medical term. Is there a good way to identify where we actually he's an ultra cool dwarf star? He is. That is true. Is there a good way to identify where we actually need to use the Feynman technique? I don't know. I think that whenever you see situations that the derivative shows up somewhere else, right? Is that kind of it? Where like if I took a derivative of the integral, it would make it easier to do the integral?
Sometimes. So usually my go-to is definite integrals. It only works on definite integral.
Only works on definite integrals.
Don't worry about it. Technically, you could do it on an indefinite integral, but because we're taking a partial derivative, we're gonna have a function of alpha that pops up, and so then you would have to do like PDE stuff to figure out what that specific function of alpha is. Mm-hmm. And normally the integral itself isn't going to give you enough information about the boundary conditions to solve that. But usually, right, it's a lot of the time, it's anytime the partial derivative would give you a simplification. So like in this case, we see that, right, the alpha, right, it gives you a simplification by getting rid of that ln of x and making it integrable. And then, yeah, I mean, kind of the idea of Feynman's trick is you're basically turning an integral into a differential equation with respect to your parameter.
And it's a simple differential equation, right? Because this is nice and separable.
Yeah, and then, or like for the e to the negative tan theta one, that one's one of my favorites, and it's the idea of that is also as well, right? You want to set a parameter alpha and then turn it into a differential equation with respect to alpha by taking partial derivatives that make it so that you can integrate the original expression in some way, shape, or form. And
yeah, I thought this was cool how this is basically, you know, very, very baby calculus of what's the power rule for integrals. And you're like, oh, it's literally alpha plus 1 divided by alpha plus 1. Yeah,
exactly. It makes it really simple. And technically, you could solve, some people say any integral with Feynman's technique, as long as it's definite.
Because you could find some clever parameter that makes it work.
Yeah, it's just how easily, like, I know there's a derivation for the Gaussian integral with it. I just forget what it is, but the idea is that you can literally choose any function to put inside of that integral, you know, and if it works out with your boundary conditions, right, as long as you can choose a specific value of alpha that gives you your original integral, and you can solve that I of alpha, then you've, solved whatever your problem is.
Mm-hmm. Yeah, it's very cool. But then you have to integrate again, right? So you're taking the partial to get something like that you integrate, but then once you're there, now you have a differential equation that you have to integrate again. So you have to, it does have to like line up. The things you pick have to be nice things that are easy to take integrals of.
Yeah, I mean they have to work out, but I mean, sometimes you don't even have to take the integral again. Like with the e to the negative tan theta, you don't even actually end up integrating. You just solve the Helmholtz equation.
Oh, okay. The Helmholtz equation.
It's just
Have we done that one? Have we done the e to the negative tan theta one? Have we done that?
I think so. Let me check. I'm pretty sure we have.
Fembox's question using triangles. Find the shaded area. What are the special things about this though, Fembox? I'm curious. Do I know anything about where the points are? I'm so curious. What's going on here? Don't I need to know, like, for instance, like, this is the same as this or something? Can I literally just find this shaded area? I'm assuming you're saying that the area of this is 15 and the area of this is 8. The bounding figure is a rectangle. Okay. And then that's it. Okay.
Yeah, it looks like we saw that somewhat.
Let me see.
And in chat.
Nice.
The pi over 2 value specifically.
Oh,
pi
that
over
was
2
that was a second
easier.
derivative. We had to take the derivative twice there.
Yeah, because by taking it again, you got the secant squared term that made tangent into just an e to the u.
Oh, that's super cool. And then it's a second order differential equation. And then I see. And then we had to go do integrating factors. Or no, what is this method called? Sorry, with the Wronskian and stuff.
That was variation of parameters. You can also solve that one with Green's functions as well.
Yeah. There are 3 straight lines inside the rectangle. Oh, I do see them. You're saying this is a straight line, this is a straight line, and this is a straight line? That's all I'm told? Okay. I'm guessing I have to draw auxiliary lines. Always do somehow. Here, let me make this like look a little nicer. Not saying your drawing isn't nice, Fembox, but let me make it look a little bit nicer.
I'll say it for him. It's not that nice.
It's fucking garbage.
I'm not saying I could draw it better. I'm just saying that it's...
I can draw it better with the aid of computer software. Okay. So we're saying this is a straight line. Oh, no. Straight line. This is a straight line. And then... I don't know. This is also a straight line. I could have drawn it better, but I chose not to. Okay, fine. You're saying this has an area of 15. This has an area of 8. And I'm curious about the area of this. Okay. Well, I know. Let's call this X. Let's call this X. Let me call this A. Let me call this B. So I know 1/2 AX is equal to 15. Right, base height, whatever. Cool. For this one, I think I want to identify this as something. Let's call that C. So then this thing right here, or let me use a different color. I am going to draw an auxiliary line, right? Kind of. So this would be X minus C. Okay. So what I'm looking for is if I want the area of this. So I want 1/2 base, so A plus B, times the height, X minus C. I'm trying to get. And I know that 1/2 AX is equal to 15. I know from this that, let's use the pink one. 1/2 BC is equal to 8. Okay. Maybe let's foil this. See what happens. Something nice happens. I don't know. So I get 1/2. We're gonna get AX minus AC plus BX minus BC, right? Ooh, I already see some cool stuff. Okay, so first of all, 1/2 AX, that's equal to 15. Okay. Got that part. That part got done real quick. So that's 15. And then we have minus 1/2 AC. I still don't know that. And then plus 1/2 BX. I still don't know that. But I do know that 1/2 BC was equal to 8. So this is minus 8. Variation of parameters is a nice topic. It is. Yeah, it is cool, Kaushik, yeah. Okay, cool. Alright, so you are here. What is up, good sir? Okay. So then this is gonna be 17. Okay, let's see. Maybe 1/2 BX is equal to something. 1/2 BX would be...
Shouldn't it just be 7?
Yes, I don't know why I wrote 17.
Bruh.
Thank you. Thank you. 15 minus 8 is not 17. Alright. AC. That's kind of a weird one. Ooh, wait a minute. This whole thing is 8. I want to say this plus this plus this has to be 1/2 X times A plus B. But do I know what that is? Do I know what that is? Oh man. Is there more on the right I can't see? There's just this. That's all there is. So we're trying to find the area of this, given we know the area of this is 15, and the area of this is 8. And so what I did is I assigned some variables to different things. So for instance, I know that if this is A and this is X, then this is 1/2 AX, which is equal to an area of 15. And then this must be 1/2 BC, which has an area of 8. And so then the area of this thing has to be 1/2 the base, which is A plus B, times the height, which if we said this was C, this height is now X minus C. Right? Do we know how much energy is in a single dimensional string? Asking for a friend who wants to find subspace. Oh, sensation. These are good ones. Asking for a friend who wants to find subspace. Is he trying to sublet? Okay. Oh,
Try factoring the 1/2 AC plus 1/2 BX on the bottom. I don't have paper nearby, but I feel like that factors into the area of that.
yeah, that's what I was about to say.
Because X minus C is going to be your height, and then A plus B would be your
Wait.
Mike.
Minus 1/2 AC plus BX is what that is. All right. Well, well, no. The minus would have to go on the side too. AC minus BX. Yes,
I
math
think if
tutor.
you set it as plus 1/2, and then
There's still gonna be a minus sign though, no?
well, you would factor the minus in, and I want to.
I see something cool with this though, right? Do you see how like this
Yeah.
area and this area plus this must equal the entire area of the rectangle?
Mhm.
Okay. And this has a height of oh, wait a minute. Wait. Oh, wait, so wait. 15 plus 8 plus 1/2 of this triangle, which is 1/2 A plus B times X. That has to equal the whole area, which is equal to X times A plus B, right? See how that plus this has to equal the whole thing? Okay, I think I do have it now. So 23 is equal to 1/2 X times A plus B. Where's my C in there though? I think Gold has it. Wait, no, he doesn't.
You're forgetting one triangle.
Am I? Oh, you're
Yeah,
totally
there's
right.
whatever the farthest right one.
Oh, I forgot about this. Oh, okay, the 8 is not the whole thing. The 8 is only this.
Yeah, the 8 is just that top part.
Damn. Okay, well, whatever. We can add that one in as well. Let's just do it. Maybe that's where my A plus C comes in. Sorry. This triangle, this triangle, this triangle, and this triangle. But I don't have a marker for where this is. Uh-oh. I really don't want to introduce another variable. I don't want to do it. Oh, wait a minute. No. Ugh. Yeah, wait. How do I get this? How do I get this triangle? You can get it? How? B is this whole thing here. A is this whole thing here.
You could.
Yeah, I gotta put in another variable then, because I need something for this. Top right triangle minus 8, all divided by x over 2. Top right triangle minus 8. So you're saying this triangle minus 8. Oh, okay, wait. Okay, wait. I think I might see what he's saying. Oh, yeah. Wait, one sec. Almost have it. Sorry. So this triangle plus this triangle, this whole triangle is b times x. Yeah. Right? This whole triangle here is 1/2 b times x. all equals that. And then, yes, you are so right. There's another relationship I have. Well, I could find the area of this triangle. I don't really think I care about that one. Wait, yeah. 15 plus this plus that is equal to that. So 15 plus 1/2 bx is equal to 1/2 x times a plus b. Oh, wait a minute. Oh, okay. Okay. And 1/2 ax. I have 1/2 ax. That's 15. Plus 1/2 bx. Oh, I just get 1/2 b. Just get 1/2 bx equals 1/2 bx.
No, the 1/2 bx is canceled.
Yeah.
And the 1/2 ax stays. So
Oh, you're right,
good.
actually. Yeah, but that already gives
1/2.
me ax equals 15, which is I already know that. No new information, unfortunately.
Oh, yeah, it does.
Man, these questions always bug me, dude. What are we solving for? We're solving for the area of this triangle down here, I think. Yeah. So in that case, I need 1/2 of this times this, I think. I think I'm starting to see it. Maybe we can do something with this triangle. Let's try that. Okay, one sec. So, this triangle, which is 1/2 x a plus b, that's equal to 15 plus 8. And then here, I'm just going to call this missing area D, for instance. Okay. Now, this area is equal to this triangle minus D. Aha. Wait a minute. Okay, so this, the thing I want. So the 1/2 a plus b x minus c, that's the same thing as this big triangle, which would be 1/2 a plus b times x, right? Base times height. And then we would say minus d. Yeah, I think I might have it too, Fembox. Okie dokes. And 1/2 x a plus b is equal to 15 plus 8 plus d. Oh, okay, got it. So this is 23 plus d minus d. Cancel.
Emotional, damn it!
Answer is 23? Is that correct? Is answer 23? I think answer is 23. I'm waiting for Fembox to tell me yes or no. Correct. Yes.
That's dope.
I was thinking it was a joke, but I was gonna say that we could just hope and pray that if you add the areas, it works out. And
Apparently it did.
yeah, it would have worked out.
Wow.
Next week.
Okay, so I actually didn't need any of this nonsense here. I just needed to believe. Okay, so we actually didn't need any of this. We just needed this. Cool. Cool question, Fems. Where's that student who was asking about dipoles, dude? Electric field due to dipoles? That's a good question. Did you submit it? Did you submit it for me? IDK man? Maybe that was him. Okay, this was Femvox. So nice. So a nice way to see it is that any triangle with equal base and height has the same area. Yeah, it is pretty cool. This is my new insult. What's your new insult, Sensation? Apparently this should have been able to have been completed in 8 minutes. I don't know how long that took us, but I feel like it took like more than 8 minutes. All right, what's your insult here, Sensation?
Come and get one in the Yarbos! If you have any
What movie is this from, dude?
you eunuch jelly thou!
This looks like something from A Clockwork Orange, honestly. Where is this from? Motion, what's up, dude? So the butterfly's wings are equal. Yes. That's pretty cool, Femfox. All right, let me see what else was in our... This is my live stream. What was in the queue? IDK man. How do I algebraically find the... Here we go, sorry. How do I algebraically find the equation of a surge function? Ax minus x e to the minus b x minus c plus d that intersects 2 points and has the right shape as this. Is it possible? Yeah, eunuch jelly though. Yeah. I feel like you need at least 3 points for a curve, no? You gotta think about how many unknowns you have here, sorry. So you have B and C being unknown. So if you have 2 unknowns, you need two equations or 2 points, right? So 2 points would be okay. Oh, but you have D as well. You have 3 unknowns at this point. So no, you need 3 points then. And that, is it kind of the same thing, right? With like systems of equations and finding and curve fitting? I think of it like, so a linear equation. It's just y is equal to ax plus b. You have 2 unknowns. So I think having 2 points gives you 2 equations. But if you have something like a quadratic, which is like a curve, now it's suddenly ax squared plus bx plus c. So now you have 3 unknowns. Yeah. So in this case, you need 3 points. So for your surge function here, which I think might have some typos in it. I don't know why it's x minus x. Sensation, what movie is that from? I feel like this is an unknown, this is an unknown, this is an unknown. I don't know what this is.
That might be a boldface X.
Oh, okay.
It almost looks like a boldface X, but maybe I'm just like schizophrenic.
Maybe he's still recovering from the sunburn.
A little bit.
Are you mobile now? You're still healing?
Yeah. No, peeling.
Oh, peeling.
Like my back just looks like, it looks like scales of just like skin.
You have dragon scale on your back?
Yeah, and it's been 11 days now.
Wow.
Yeah.
You're about to look like King Baldwin of Jerusalem, dude.
Yeah, it was pretty rough.
What's up, Zach?
At least most of it's healed. I don't feel the sunburns. I just, especially like anytime I sweat or shower, it's just like dead skin just falling off everywhere.
No. Well, at least you'll have a nice tan, maybe, or not. Definitely an increased chance of skin cancer.
I didn't even really get that much of a tan. If I like really burn, I don't tan. I only tan if I get like light burns. But like I was tan for like 2 days and then all of that skin peeled off.
Yeah, it just goes off. Wow. I feel you. What's up, Zach? Yeah, sorry. My internet, dude, yesterday was like acting up. I was really upset. So I'm sorry you guys couldn't see my lecture on potential. Also, it wasn't like that great of a lecture because I literally gotten off the plane like an hour beforehand and my brain was already just like fried. I was like, no more. I don't want to do any more stuff. I logged in a while ago to chastise you on writing a janky integral symbol, but you fixed it. Thank you. So you just lurked. We've been having a fun time. This was a really fun question that we did. Breasticles gave us. I think it came from your server, he said.
Yeah, actually, it was basically Winklebot that gave us this question.
Winklebot. So this one was fun.
Yeah, I just took it from them.
And then this was another fun one from Kaushik Techno, which had like some integration stuff in it. I helped out a student with Taylor expansions and finding the electric field of a ring and a point charge. And then we did Fembox's question with blessed triangles. I did some problems in chapter 3 fields and circuits that potentially... Ooh. Yeah, let me know how you guys' E&M study class is going. If you need me to like hop in and help out with any of the potential questions, I can definitely show some stuff. But otherwise, yeah, I think we're out of time, so that's good. These days, I have to like teach 2 hours of lecture, and then I have the 2 hours of office hours. Like, my brain's done after 2. After 4 hours of physicsing, I'm like, no more.
You done messed up, Aaron!
No more. And I gotta go grade stuff now. But that being said, make sure go check out our streaming schedule. I am gonna add some office hours times for Thursday and Friday. I will also add probably some chess games as well. I'm gonna go eat some dinner. I'll add all this stuff. I literally just got back yesterday. And then looks like, yeah, Zach's got his E&M study group tomorrow. That's fun. Then more math stuff on Saturday. Upload your brain to AI. I mean, just the good parts, not the soccer stuff. Not, what is Sensation called? The Rainbow Squad stuff. So, yeah. Oh, and it looks like Zach's got another episode of 16. Nice. That'll be fun. I got so close on that last episode. I lost an insane amount of points because I got really nervous on the last question and I read it wrong. And I put like, it was like pronation and supination, and you were just asking for the body part. You wouldn't I thought it was a harder question than it was. And so I couldn't make those points back. But congrats to Kevin Does Chemistry. He outplayed me there for sure. Anyways, have you heard of Eric English, the 16-year-old promoting peptides and hopped on roids? There's always someone doing that. That's not a new thing, dude. There's always some dude back in my day, bro, dude. Who remembers Z's, dude? This was the ultimate. This was the ultimate like young kid hopped on roids and stuff. People remember Z's. He was my generation's version of like your clavicular basically, but I think without the misogyny and stuff. But he ended up dying of a heart attack, I think. So yeah, those things eventually will get you. So don't do them. Cool. All right. I gave the advanced answer. I did give the advanced answer. I get E points. All right, let's go to the stream. All right, thank you everyone for coming to Actual Education Office Hours. Appreciate all the questions today. Again, remember, if you ever want to know when we're streaming, we have a website, actualofficehours.com. You can go there, submit your questions as well, and we'll get to them at some point. Are you Myron Bra? There you go. Live fast, die young. Leave a good-looking corpse. Yes. I say my motto is, was it? Die young as old as you can. I think that's the quote. I think that's what it is. Yeah. So, it basically means like try to stay active and don't rot, but do it as long as you can. All right, let's go raid someone on Twitch. We're gonna go say hi to. Yes, always good seeing you guys. Appreciate. I'll make some announcements for the streams on Thursday and Friday. Who are we following? Who's up? Having fun. Casey Snow Arts talking about art development and Schnicks. I love Schnicks. Schnicks are cool. Moo Hoodles is going to play Doom. Skittish is doing prom night. This is so fun. I met these people actually. Here. Let's go say hi to Casey. Casey's great. All about Schema. All right. They're probably at the end of their stream, but go say hi to them. Cool. All right. Enjoy the rest of your Thursday. Or Wednesday, sorry. We will see you tomorrow on Thursday. Peace.